Hello everyone, my name is Gabriela Herrera Altamira and I'm going to present our work on EEG modulations induced by a visual and vibrotactile stimulation. Brain-computer interfaces are a promising technology for post-stroke motor rehabilitation. They can be controlled through kinesthetic motor imagery or KMI, which is a very suitable technique for post-stroke patients who can no longer perform the movement but can imagine it. More specifically, for KMI, we're going to focus on recalling movement sensations such as pressure, temperature, texture, muscular contraction, and/or nerve activation. KMI is interesting because it modulates sensory motor cortical activity, it enhances motor performance, and it aids primary motor cortex rehabilitation. However, it has a big challenge, and it is that it lacks kinesthetic and sensory feedback. Therefore, it's very difficult to learn and to execute. To address this issue, different feedback modalities have been proposed, such as visual feedback, functional electrical stimulation, robotic orthosis, tendon vibration, and more recently, tactile vibration, which involves stimulating the mechanoreceptors on the skin. However, very little work has been done involving tactile vibration and post-stroke rehabilitation. It has been demonstrated that vibrotactile stimulation enhances motor imagery as it elicits activity in mu and beta frequency bands. However, in most of these studies, the stimulation was given at the same time as the participant was performing the kinesthetic motor imagery. So the question rises on how to distinguish the EEG activity coming from the KMI and the EEG activity coming from the response to the stimulation. Moreover, vibrotactile design choices are often unclear. For instance, when there is more than one vibration motor, the activation and deactivation order can be different. For example, as proposed by this study by Jeanette, all motors were activated and deactivated at the same time in a simultaneous way. On the other hand, as proposed by Lieb in 2013, they can also be activated in a sequential way, either point by point or in a sweep. So far, there have not been studies comparing a simultaneous versus a sequential activation order, and we do not know the impact of any of these two on the EEG activity and if there is a difference from using one or the other. In addition, in most studies, the vibration intensity has always been fixed, meaning that it was always the same, regardless of the performance of the participant. But we can also give different intensities that are related to the participant's performance to give a more detailed feedback and so help the participant to improve. We can expect to observe differences in the EEG responses due to different vibration intensities as it has been demonstrated in fMRI studies. So, taking into consideration the lack of studies comparing simultaneous versus sequential activation order and the lack of studies using different vibration intensities, we performed the next experiment. Our objective was to investigate the EEG modulations associated with a bimodal stimulation comprising a visual and vibrotactile stimuli. We compared 4 stimulation intensities and 4 vibrotactile device configurations. We recruited 18 neurotypical healthy participants. They were all right-handed, so the stimulation was given on the non-dominant limb, and their mean age was around 26 years old. We recorded EEG signals using a biosemi-active 2 system with 64 electrodes and a sampling frequency of 2048 Hz. Concerning the bimodal stimulation, for the visual component of it, we used this non-immersive virtual reality interface that had a hand grasping a ketchup bottle to put sauce on a hot dog. There was also a traffic light to give indications to the participants, and a judge that would give a little bit more of information about the stimulation level. For the vibrotactile component of the stimulation, we developed this vibrotactile device. which actually consisted of 3 eccentric rotating mass 10 mm coin motors that were fixed on the upper limb of the participants using these adjustable straps, and the motors were contained in these 3D printed cases. One motor was placed on top of the hand, so it was called the hand motor, and 2 motors were placed on the forearm. The extensor motor was placed on the posterior part of the forearm, and the flexor motor was placed on the anterior part of the forearm. All 3 motors were controlled with an Arduino Nano that was contained in this 3D printed case. All participants tested 4 device configurations. One of them was a 3-motor sequential configuration, where the flexor motor was the first one to be activated, followed by the extensor, and finally the hand motor. For the 3-motor simultaneous configuration, all 3 motors were activated at the same time. Then, for the 2-motor sequential configuration, the flexor motor was the first one to be activated, and then the hand motor. And finally, for the 2-motor simultaneous configuration, all 2 motors were activated at the same time. As I said before, all participants tested each of the 4 device configurations, where each configuration represented 1 run of the experiment. As I mentioned before, we compared 4 levels of stimulation, and each level was presented 4 times to the participants, summing up to 16 trials per run. We started with what we call the none level, where there was no vibration given, and for the visual component, the hand would press the bottle, but no ketchup would come out of it. We increased the vibration and the visual until we reached a high stimulation level, where there was a high vibration intensity and a large quantity of sauce. As you can see here, the duration of each level was also different, and this was because in real life it takes longer to put a larger quantity of sauce on the hot dog. So by varying this duration, we expect to add realism to the stimulation. Additionally, these 4 levels were pseudo-randomized, so participants did not know what level they were going to be presented with next. This is a timeline of 1 run of the experiment. Participants started with a resting phase of 30 seconds indicated by this red traffic light. Then it changed from red to red and orange, indicating a warning phase, and then when it was orange, the stimulation started. Here you can only see the visual component of the bimodal stimulation, but the vibration was also activated at the same time, so they were both synchronized. When the stimulation was over, a resting phase of 5 to 7 seconds started, marking the end of 1 trial, and a new one started with the red and orange traffic lights. As for the EEG offline analysis, we used EEG Lab. We started by performing a common average referencing, followed by a high-pass filter at 1 Hz, a notch filter at 50 Hz, and a low-pass filter at 256 Hz in order to downsample the signals to 512 Hz. Then we performed an independent component analysis to remove eye and muscular artifacts. We proceeded to extract the epochs corresponding to the beginning and the end of the bimodal stimulation, and finally we computed the event-related spectral perturbations. Now let's take a look at the results. The first thing we did was to compare the device configurations for the alpha and low beta frequency band. We observed that whether we used 2 or 3 motors in a sequential or a simultaneous way, there was no significant difference across configurations. Then we performed the same analysis, but this time for high beta, and we also observed that there was no significant differences across the configurations. But let's remember that we also had 4 levels of intensity, which we also compared. And here are the results. First, concerning the alpha and low beta frequency band, we observed that there was an ipsilateral event-related desynchronization that emerged at the medium and high stimulation levels. As we expected, we observed contralateral ERDs across all stimulation levels, and we also observed some posterior activity that might correspond to visual processing of the virtual hand. Then, for high beta, we observed that the ERD was present during the low, medium, and high stimulation levels, which happened to have vibration, whereas the non-stimulation level had no vibration at all. We observed that there were statistically significant differences across all stimulation levels for both frequency bands, so we performed the pairwise comparisons to find out these differences. First, for the alpha and low beta band, we observed differences between the non and the medium stimulation levels, and the non and the high levels. Then, for high beta, we observed differences between the medium and the non, and the medium and the low stimulation levels. We also observed differences between the high and the low, and the high and the non-stimulation levels. Altogether, these observations suggest that the medium and the high stimulation levels are very similar. During a time frequency analysis, we observed that there was a transient event-related synchronization, but only at the beginning of the stimulation. So we computed the topographies corresponding to the first second of the stimulation, and we observed this ERS mainly in the medium and the high conditions, and we can see that it is very centralized here. So how to explain this? Well, we know that delta is present during continuous attention tasks, and a previous study suggested that vibration increases attention. Therefore, taking into consideration these two key elements and our observations, we might say that attention may depend on the vibration intensity. However, in order to confirm this hypothesis, another study must be performed where we really evaluate the impact of vibration on attention. Finally, to summarize, let's remember that our objective was to investigate the EEG modulations of the bimodal stimulation, including visual and vibrotactile stimuli, across 4 device configurations and stimulation levels. We did not observe differences in the EEG among the device configurations, and we observed that the bimodal stimulation elicited bilateral ERDs in the somatosensory cortex. Moreover, we observed that the ERDs exhibited variation depending on the stimulation intensity. That is, the higher the intensity, the larger the ERD was. In future work, we are going to incorporate the bimodal stimulation into our functional KMI-based BCI. We are going to assess the impact of this new bimodal feedback on BCI performance and user experience. As we saw that the bimodal stimulation elicits activity on the EEG, we are going to give the feedback in a delayed manner. That is, we're going to wait until the participant finishes performing KMI to avoid superposition of brain activities. That is all for my part. Thank you for your attention, and let me know if you have any questions.